All right, so we have our periodic table and our formula sheet. What we really need on here are the polyatomic ions and these solubility guidelines. So today is April 6th, and we are learning about net ionic equations. All right, when we do these, there's a specific order. We go in. Yesterday, when you worked on the lab, you wrote out the molecular equation. So what that is a balanced equation with states of matter noted. And how we note those were solid, liquid, gas, AQ for aqueous solution, we had some questions in a previous class. What's the difference between a liquid and an aqueous solution? If it's liquid, it's a pure liquid, nothing dissolved in it. That would be like water. Also, hydrogen peroxide is considered a pure liquid with nothing dissolved in it. Aqueous solution, we'll just put stuff dissolved in water. After you have a balanced molecular equation and all of these states of matter are noted, the next thing you do is called a complete ionic equation. The complete ionic equation shows every single ion with its charge and state of matter Once you have this complete ionic equation, then you'll go to the net ionic equation. This shows only the ions and product involved in the chemical reaction. No spectator ions. So what are spectator ions? We think about spectators if you go, let's say, a football game or a theater performance. Those are the people watching. They're the spectators. They're not involved with the performance or the game at all. So those, we'll just put not involved in the reaction. All right, the best way to do this is through, to see an example. Those of you who have sloppy handwriting, you need to really pull it in focus here if you're going to get everything organized how it needs to be. Get this out of the way. Okay. All right. We're going to go with lead 2 nitrate. And we're going to start by writing this out. And sodium phosphate. On a quiz or test, they would give you these reactants and say, predict the products, write the molecular equation, the complete ionic equation, and then the net ionic equation. Tell me the spectator ions. This is how you need to start it. First, we got to get our reactants and write proper chemical formulas. Charge of lead 2, the 2 tells us the charge is +2. Nitrate, you would look on here, and the charge is -1. Sodium, we go to the periodic table. It's in the +1 column. And phosphate, I'm going to go to my formula sheet. The charge is -3. So off to the side here, I'm going to note what I'm doing first. This is the molecular equation. Okay. The formula for lead 2 nitrate, you need 1 lead and 2 nitrates. 1 lead and 2 nitrates. Now, we can assume they're giving us products here that are aqueous, or we could look at our rules. So, all of these, if you want to make yourself a little note, sodium, potassium, ammonium, and nitrates, those all are aqueous. Okay. So when I have lead nitrate, nitrates are aqueous. So after this, I put AQ. That is an ionic salt that dissolves in water to make an aqueous solution. Next, my formula for sodium phosphate. I need 3 sodium for every 1 phosphate. That is 3 sodium and 1 phosphate. I look at these rules. Anything with sodium is aqueous. All right, now we have to think. Looking at our reactants, who's going to hook up with who? Okay, so these are dating, and we've got some things that are going to be unfaithful. So the positive always gets with a negative. So lead 2 can get with phosphate, and sodium can get with nitrate. Remember when you write it, you would write it sodium nitrate, not nitrate sodium. The positive always goes first. So let's do that lead 2 phosphate. Lead has a charge of +2 and phosphate's -3. So I use the cross method. I'm going to need 3 leads, 2 phosphates. Three leads, 2 phosphates. Now I go to my solubility rules. Do you see the words lead or phosphate on there? So it's not aqueous. That must be our precipitate. It's not on the solubility list. Soluble list, I should call it. Now, we took care of lead phosphate. What's left over? Sodium nitrate. This has a charge of +1. This is -1, so you only need 1 sodium for every nitrate. Sodium nitrate, both of those are soluble, so that'd be AQ. Last thing I need to do for this molecular equation is balance it. Let's see. I've got 3. If I put a 3 here, it'd be 3 nitrate, but there's a 2. If I put a 2 here, now I have 6 sodium. I put a 6 here, 6 sodium, 6 nitrate. Put a 3 here, 3 times 2 is 6. 3 lead, 2 phosphate, 2 phosphate. So by doing that, now I have a balanced equation, states of matter noted. This is my molecular equation. Our next step is then a complete ionic equation. Yesterday when we were doing the lab, you did particle diagrams and you knew, since this was aqueous, when the lead and nitrate go into solution, it dissolves and you got leads floating around and nitrates floating around. And the ratio was for every 1 lead, you had 2 nitrates floating around, right? So when you do the complete ionic equation, we are showing the ratio and how they're floating around as ions. This 3 applies here, but we also know it applies over here. So the first ion, I'm going to note and write teeny tiny. This is going to take us all the way across the page, and I'd like to keep it on one line. We have 3 Pb, and each of them have a charge of +2, and those are dissolved in an aqueous solution. Then, for nitrate, 3 times 2 is 6. So I have 6. Nitrate had a charge of -1. So for every 3 lead ions floating around, I have 6 nitrate ions floating around. Sodium, 2 times 3 is 6. Each of the sodium have a charge of +1. And phosphate, you have 2 of. Phosphate has a charge of -3. I'm going to zoom in on that so you can make sure you got everything accurately written down nice and neat. Those are aqueous. They break in, they dissociate into ions in the liquid, in the water. We mix them together. And now let's look at the product side. This is a solid. When you mixed them, you got this solid that either settled to the bottom or you put it in a centrifuge and force it to settle to the bottom. It does not break into ions. It is not dissolved. So you keep it as one unit. Do not break it apart into ions. This is aqueous, so we do break it apart into ions. It says 6 sodium. Each of the sodium have a charge of +1. And 6 nitrate. I'm barely going to fit this. All right, that is the complete ionic equation. That's why when we wrote the definition, we said it shows every single ion. Took me across the whole page there. Next, let's identify our spectator ions. Spectator ions are when you look to the left and right of the arrow. They're exactly the same. So I see 6NO3 minus 1AQ, 6NO3 minus 1AQ. And then I see 6Na plus 1AQ, 6Na plus 1AQ. So our spectators must be, which is sodium ion, and nitrate. We can now wrap up with the net ionic equation. We remove the spectators and write only the things involved in the reaction. So if I didn't circle it, I'm not going to include it. That is the net ionic equation. Now, why would we do this? Why go through all the work? Let's say there's a lab I want you guys to do, and it calls for lead 2 nitrate and sodium phosphate, right? So I look in the back. We have no sodium phosphate. I really want to do this reaction, though. I can do this and go, oh, sodium's only a spectator? Sodium's not involved in the reaction? Okay, well, what can I substitute in its place? I could substitute lithium, potassium, rubidium, cesium, right? I could just substitute that. It's only a spectator. It's only floating around in there. So if I run out of sodium phosphate, if I have lithium phosphate, the reaction would occur the same. If I had potassium phosphate, the reaction would occur the same. Now, can I just swap out the phosphate? No, clearly that was involved in my reaction, if that's the product I want. The spectators were just floating around before and after.